So like I was saying, this is a moderately interesting lecture. I shouldn't undersell my lectures. But we're getting into the question of how you actually schedule processes. And so this is the one where we cover sort of like the common basic ways that people approach this problem. And then next time, the reason why I'm so excited about next lecture is we actually talk about some really interesting results from real-time process scheduling, and also all the wild things that the Linux schedulers have been doing over the last couple of iterations of the kernel. And the Linux kernel is a really fruitful bed for exploring these alternate approaches. And so it's really kind of fun to talk about. There's some advances that people have made in scheduling algorithms that they've been exploring there. So when you have a commercial OS, you don't have as much flexibility in exploring those things. So basically, obviously, this is all about how do I share this common resource of the CPU, or CPU plural, if you happen to have multiple CPUs to manage. But this is one of the big responsibilities of the OS, and so we'd like to have multiple concurrently executing processes. Most OSs need that. And so if we have situations where some are waiting on I/O, others can be doing CPU-based work. And so this is a really nice thing when we have, they call it a process mix. And I think I mentioned that earlier on in the term, like probably in the first week, that a good process mix means you have some processes that are doing I/O, they're blocked on I/O, leaving the CPU available for other processes. And then ideally those become blocked on I/O, and other I/O blocked processes are now available to start working on the CPU. So that means that processes fall into various states: running, ready, and then of course blocked, but I don't actually mention this right here. Running is on a CPU. Ready is, if I had a CPU, I would be able to run, but I don't have a CPU. So you have those two. And then of course you have blocked, you have many different blocked states depending on what you're blocked on, and you may have a terminated state and so forth. So the question of scheduling is, how do we allocate CPU time to these various processes that can actually run? So that's why only these are listed, because these are the ones I care about. Okay? They couldn't even have a CPU if they were, there would be no point in giving them a CPU because they can't run at all. So this was the picture. Again, I think I introduced this picture previously, but we have new processes coming in. They go into the ready queue because they're ready to go right off the bat. They do things on the CPU and either get preempted, or they yield, and then they can go back to the ready queue, or they can go into one of various other queues based on if they're suspended or they're blocked on some long-running operation. And the thing here is that you have various schedulers. That's the thing that I want you to look at this time. Long-term scheduler, medium-term scheduler, and short-term scheduler, which basically, in computers that have these things, will allow you to control processes over varying time scales. So the long-term scheduler introduces processes into the process mix. So you'd see that in a batch processing system. Same thing with the medium-term scheduler. If you don't have a good process mix, everybody wants a CPU, then it could suspend some processes and maybe reduce context switches so that they can get things done more quickly. Or if we have too many processes blocked on I/O, suspend some I/O block, introduce some new processes, hope that maybe you get a better process mix. We will be focusing on the short-term scheduler, because the short-term scheduler is the scheduler that everybody has now. We don't really have medium and long-term schedulers unless you're building a purely batch processing system. Okay, let's see. Also, kernel, as you're probably all discovering or encountering at this point, because you don't even have user space yet in Pintos, is that we're scheduling kernel threads. We kind of observe a kernel thread. Processes are always associated with one or more kernel threads, and so obviously the kernel thread will behave as the process behaves because it's the thing that gives the process its life. So, like you say here, scheduling occurs within the kernel. In kernel mode, the process's user context has already been saved at that point. So there's not even, it could look at the process, and it could certainly look at how the process behaved and how it ended up in the kernel. But at this point, we're in the kernel thread itself. We're the kernel thread proper. Okay? So typically, there's one entry point that does the switch. Okay? So you have, for example, a schedule function, which is a nice simple thing. You probably recall that even in CS24, in our little user space threading library, we had sthread schedule that would be called, and that would pick another process, or in that case, a user thread, and then switch to it. Okay? So one entry point. And this is kind of a fun one, because in a given kernel thread, if you're looking at that kernel thread's perspective, it sees it calling schedule and then leaving schedule. But something happens in between. It has a blackout, basically. So we switch to somebody else. They run for a while, but what their perspective was is they called schedule, and then eventually they leave schedule. So everybody sees themselves entering and exiting schedule. Okay? It's kind of a fun thing. It's this wild little detail that goes on inside the OS. Okay? Usually what happens is we call it with one thread and leave with a different. There's one situation where we might call it and then leave with the same thread. That's if you had priority scheduling and the highest priority thread was yielding. And it's like, well, you're still the highest priority thread. Get back to work. Or if you have a situation where there's only one thread running. And then that thread, maybe it gets preempted or it yields or something like that. And it goes back to running because there's no other thread to choose. Okay? That's basically the only time that you have one thread that's always the entering and leaving with nobody else in between. Now, there's two tasks that occur here, and both of these are pretty obvious when you think about it. One is who gets to run next, so there's a choice made. And then secondly is, okay, well, if it's a different thread, then we need to change contexts. So there's a context switch that has to occur as well. The second part is called dispatching. Okay? Dispatching has to be as fast as possible. This is an unavoidable overhead in thread execution. Okay? We have to figure out how to switch to it. And you can imagine that this could be expensive because, like I have on the slide, I have to possibly change memory mapping. If I change memory mapping, again, you should always think to yourself, if I change the memory map, what else happens? Well, I have to invalidate the translation look-aside buffers because now they need to start looking up entries on the new mapping. Okay? Probably caches are going to become useless as well because that new process's data may not be in the processor cache yet. So, expensive, but it's unavoidable. So you do what you can to make it as fast as possible. Let's see, now the kind of fun thing about thread switching is that it actually tends to involve three threads. So if you look at the Pintos thread switch function, which you can track down relatively easily, you'll notice that it says switch threads, current thread, and next thread. Okay? And so current is the one we're switching away from. It's me. Next one is the thread that the scheduler chose. This is the one that we want to return to. And then we also return a third thread. And it's like, well, why is this going on? Okay. Now, one interesting and important detail. So notice I have here, I'm switching from thread A to thread B. So somebody calls switch threads. On thread A, they call switch threads A to B. Okay. Now, the question is, what happens after the context switch? What do you see after the context switch? So it says this function switches from thread A CPU context to thread B CPU context. So that means now we have thread B's stack, we have thread B's registers, we have all of those details from thread B. So the question is, thread B starts running, what arguments does it see on switch threads? Does it still see A and B? That's the issue. Yeah, I saw the head shaking in the correct direction. So when thread B resumes, it's going to see itself as the from thread and some other thread as the to thread. So the upshot here is that we've kind of lost thread A. Okay? And the reason why this is a problem is thread A may be terminating. We may be switching away from thread A because it's terminating, and now we need to deallocate resources. We need to free up thread A's thread struct and its memory map and all of these kinds of things. We need to clean that up now. So we need to make sure that we don't lose thread A's context in the switch. Okay, so that's the reason why we have three threads involved. We have A and B, the two that are actually involved, and then we have some third thread, which is the one that B was switching away from. I'm sorry, it was switching from B to some other thread. So basically, what happens is the function, again, the dispatcher is constructed in such a way that the previous thread context, in this case, the example, it would be A. So we're switching away from A, that we don't lose that context so that the kernel can clean it up properly. Okay? So in this case, like PINTOS is really simple. Remember that on x86, GCC, all of that kind of fun, we will always return our value in EAX, or if you're on 64-bit, it's returned in RAX. And so the dispatcher typically is implemented in assembly code because it has to be. And so the old thread context that comes in, the first argument is just saved into that return register. And that way, the dispatcher knows that the code that's returned to will still have the from threads context. It'll still have a pointer to that. Okay, does that make sense to everybody? Pretty straightforward, but it's always a little bit of a surprise when you see it for the first time. Okay, it's part of the fun of context switching. So lots of scheduling algorithms to choose from, and it's interesting because it really, like, the tool that you want to choose depends on the job you're trying to perform. So are you building a batch processing system? Are you building a little tablet with a user interface where people like to be able to touch it? I don't know. You probably have seen old people work with tablets, and they're just like, bang, it's not responding fast enough. That kind of, so responsiveness is very important, and so you can imagine that the need changes depending on the purpose of the system. So we have CPU utilization. Am I keeping the CPU busy all the time? If you're building a batch processing server, that's really what you'd want. Throughput, how many processes are completed in a given unit of time? Okay, if you have many short-lived processes, you'd want to maximize that number. Turnaround time, so how long does it take to finish a given process in wall clock time? So this includes waiting on I/O and so forth. Total time a process spends in the ready state. So the process could run, but it's waiting for a CPU. Maybe we want to try to minimize the waiting time the process is spent. Okay? And then response time. This would be like your user interface type systems where you want the process to respond quickly to input and produce its output. Okay? Or if you could even do that on a command terminal kind of context. So you can see there's a lot of different ways we could measure one algorithm over another. Okay, it really depends on what you're trying to accomplish with the system. So one interesting detail about processes is that they all have this common behavior that they have CPU bursts interspersed with I/O bursts. To me, this is not really a surprise, and I don't think it should be a surprise to you either. We do some computations, then we need more data, so we do something and it happens to be slow, so now we're waiting for that thing to finish. Like maybe we're receiving network data, and we do stuff, and then we go to the file system. Now I have another wait, and then I get the data, and I can process it. So really, it's not a surprise, but there's been a lot of research analyzing the length of CPU bursts compared to I/O burst length and so forth. So you can easily pull up that info. By the way, I know I mentioned this in my classes, but you have access to the ACM journals. You should totally use that as much as you can while you're here, because once you graduate, unless you're really lucky, or go to grad school, or maybe those are the same, you won't have access to those journals as easily anymore. So take advantage of it, like dl.acm.org or whatever. Get on there and search for OS papers or whatever kind of topics are interesting to you. Okay? So, but the research basically shows that CPU bursts tend to be short. They tend not to be long, unless you have a real compute-intensive kind of task. And so this is kind of nice. And I/O bursts tend to be rather long because it turns out that I/O devices tend to be slow. And especially if you're talking to a human being, then that's really slow. Okay? So some schedulers, we talked about this previously. We even talked about it in 24. Some are non-preemptive or cooperative. So this is just cooperative multitasking. So long CPU bursts get to be pigs. They get to hold the CPU as long as they want. Okay? So basically, you see that you only have scheduling when you block or terminate. There's no preemption. You could yield. That's certainly an option as well. Then you have preemptive schedulers where processes with long CPU bursts can be interrupted. And so this tends to be the way that most OSs work nowadays. Okay. First algorithm we're going to talk about is really boring. It's called first come, first serve. And it's basically just a queue. So you have a FIFO. And basically, new processes always go on the back, and eventually they make it to the front, and then they get the CPU for as long as they want it. Okay? So there's 3 things that can basically cause a process to leave the CPU. And I have them listed here. You'll hear this a lot. It yields, it blocks, or it terminates. So yielding or terminating tend to be voluntary actions, unless the termination is because of a bug. And then blocking is I perform I/O, and so I can't really use the CPU anyway. Somebody else should take it. Okay. So that's first come, first serve, and it's non-preemptive. You'll notice you get the CPU as long as you want it. Why am I even mentioning it? Well, because you add one little detail, and suddenly you get an interesting scheduler. If we add preemption, then you start getting round-robin scheduling. Okay? So that's really the only reason we mention this, because round-robin scheduling is a nice, simple algorithm, easy to implement, and you can actually get quite a bit done with it. Okay? So you get a fixed-size time slice, so now you either yield, block, terminate, or you're preempted, so that'll kick you off the CPU, and then somebody else gets to run. Okay, so we still have a FIFO, you still go on the back, either when you're new or when you leave the CPU, and then when you make it back to the front again, then you get to run some more. Okay. So pretty straightforward. And this time slice size is the parameter that you can tune. You can actually affect the system quite dramatically using this parameter. Remember, if you have a short time slice, then that's going to make interactive processes happy because you know that no compute-intensive tasks are going to hold them up. They'll get back to the CPU relatively quickly to handle input. But overall, you'll have a lot of context switches. So you'll be invoking the dispatcher a lot, and you get that unavoidable overhead of switching between processes. The way that I normally put it is when you're context switching, you're not doing useful work. And useful work is what the user wants you to do. So you'd like to keep the number of context switches as small as possible while still optimizing for the other goals of the system. Okay. All right, let's see. So shortest job first is another one that we have all seen because we talk about it in CS24. So in the context of CPU burst, it's really most accurate to call it shortest next CPU burst first. Because really every process is going to be executing CPU bursts interspersed with I/O bursts. So you just try to estimate how long that next CPU burst will be, and then you schedule based on that. Okay. So the idea here is that we minimize the average waiting time. Again, same example that we have from 24. So we have 4 jobs, 2 units, 4 units, 5 units, and 7 units of time in length. And if we do the shortest job first, the shortest CPU burst first, we minimize the average time to starting a job. Okay. So, nice, I guess, right? And the longest job first, for comparison, nobody does this, but that just really clearly illustrates how you can affect the average wait time quite dramatically, even though the total time you're waiting is the same. Okay? So for an interactive system, shortest jobs first is really appealing. Okay, yeah, so this is the challenge. How do you predict that CPU burst length? How do you predict what the next CPU burst length is going to be? Okay, and so normally what we do is we try to predict the future using the past. We try to look at the future, we try to look at the past and build some model that allows us to compute the future relatively easily. Here is a typical way that this is done. And it's kind of gross, and you'll notice it definitely involves floating point or decimal math, which you already probably noticed it in Pintos. You don't really get that for reasons of simplicity, really. There's no great difficulty in implementing floating point in the processor. You just have to make sure you save it as kernel thread contexts, and then that makes it slower, but processes like floating point anyway, so why not? Anyway, so we have the actual length of the CPU burst n. This is a measurement that we've taken, so T sub n, that's the actual amount of time the process previously spent, or the kernel thread previously spent. We have the predicted burst length. Notice it's tau instead of lowercase t, n plus 1. And so what we do is we have this parameter alpha, which is our little knob that we can turn. It goes between 0 and 1. And basically that allows us to decide how much we care about recent history and how much we care about distant history. Okay? So you see we multiply our measured previous cycle time by alpha, and then we have tau sub n, which is an interesting parameter. It's like, where did that come from? And that's 1 minus alpha. So t sub n is the recent past, tau sub n is the distant past. Okay? That's the idea. And so it's kind of nice. You can tune this parameter. So expanding this out, just to show you, and this is not complicated math. I don't think anyone, this is why I love teaching at Caltech, because nobody's scared of math. So you look at this one. Maybe we're all scared of math, but we face it anyway, right? So, but if you look at the tau n plus 1 and expand it all the way out, you see that, well, so you have t sub n minus 1, t sub n minus 2, all the way down to tau naught. Okay, so we have tau naught. That is our initial estimate of how long the CPU burst length might be. Maybe we say it's 0. Maybe we say it's a more reasonable value or something like that. But the bottom line is you can see that if you keep computing this value all the way along, it's a pretty straightforward computation to do, and you can use that to sort of guess the next burst length. And using alpha, you can decide how much the distant past should matter and how much the recent past should matter. And it's definitely a balancing act, because processes do change their behavior over time. Some do anyway. And so you want to make sure you have a scheduler that is flexible in, you kind of want to selectively forget the past a certain amount out, but you should definitely weight recent history more, because that may be more relevant. Okay? So this is the idea behind shortest job first scheduling. Any questions? Pretty straightforward, right? Honestly, I think your 4.4 BSD scheduler implementation that you do will do something similar to this, but obviously the model is notably different in a number of ways. Okay, so this can be preemptive or non-preemptive. If it's preemptive, then you would say shortest remaining time first. Okay? And the idea is that when you add a new job, and its predicted burst length is longer than the current thread's remaining burst length, then it would preempt the current job. Okay? So that kind of suggests maybe that tau naught should be chosen so that new threads that come in don't always just kick off the current thread. Maybe it would be a good idea to choose something nice in middle of the road so that they can come in at a reasonable time but not necessarily immediately. Okay. And also, we talk about this in CS24, we have the potential for starvation, because if you are preempting all the time, then longer running, or I should say jobs with a longer predicted runtime may be continuously preempted, and then that would make them sad. Actually, it would make them nothing, because they can't do anything at all. Okay, so you have a ready queue of short jobs and long jobs, and if new short jobs keep showing up, and you could even have a situation if there was enough short jobs, I yield the CPU, I go somewhere else, and then I become ready again, I rejoin the ready queue, and I'm still preempting that long job. So if you have this kind of situation, then basically you would have a problem where the long job never gets the CPU. Okay. So you have to figure out some way of circumventing that. Okay. And so shortest job first is an interesting example, because it is a kind of priority scheduling. You're basically saying the shorter your next CPU burst, the higher the priority. Okay. So you can think of it in terms of priority scheduling. And it is also possible to assign fixed priorities. And so, like I say here, it's typically represented as a number. It doesn't really matter if it's like higher number is higher priority or lower number is higher priority. You just pick one when you design things. Like Pintos will have a specific way that it interprets priority that you should follow. Priority scheduling can also be preemptive or non-preemptive. And this is kind of a really interesting detail. Pretty much most priority-based schedulers that I've seen are preemptive. So a new ready process comes along and it has a higher priority, then the current process is kicked off the CPU because somebody else should run. So that tends to be straightforward to implement because in the kernel you basically just say the current kernel thread says, oh, there's a new kernel thread coming in board. I'll just yield. And then if I'm still the highest priority, then I'll just get the CPU back. Otherwise, the new thread may get the CPU. So it's usually not very difficult to implement preemption in these kinds of situations. Okay. Priority scheduling, interesting detail here. We don't have preemption. We don't expire a kernel thread because it's used up too much time on the CPU. And this is both cool and also problematic. Okay? So the process holds the CPU till it blocks, yields, or terminates. Obviously, if it yields and it's still the highest priority process, then it may end up running again. And so a lot of times you want to see it blocked, like I want to sleep for a certain amount of time, or I want to go perform some long-running task, or just terminate the thread and let some other threads run. Okay. So this one is definitely vulnerable to starvation. Basically, you may have a situation like if you had a high and a low priority thread, that the high priority thread is always running, and it never gives the low priority thread a chance to run. So you kind of see the way that these designs work out, that the high priority threads run for relatively short periods of time, and the low priority threads can run for longer periods of time. Really common. So people are kind of building the system to be useful, mimicking the same kind of things that you'll see in the other schedulers. Just the design of the system will work out that way. One approach is that you can actually tinker with the priority. So you could have like a base priority and an adjusted priority based on how long it's been since I got the CPU. Okay? So that's certainly a possibility. You could do this with shortest jobs first or shortest remaining time first as well. Age processes based on how long it's been since they got the CPU so that they could actually get onto the CPU more quickly, even if there's shorter jobs. But this is the real issue, and this is the fun, dangerous, frightening one if you happen to be working with a priority-based system. Priority inversion. Okay? The idea is that a high priority process, if you have the high and the low priority process, and they both could run, let the high priority run. That's the idea. But priority inversion is something is mucking up that machinery and preventing the higher priority process from ever preempting and actually running. Okay? So has anybody seen this on a CS24 exam? I love using this on the 24 final. I don't use it every year, but I do some years. Okay? Simple scenario. You have 3 threads. High priority, medium priority, and low priority. Okay? So you have a low priority process. It starts running, and it locks a resource. Okay? Resource R. So far, so good. We're all good here. Then the high priority process starts running. No biggie. It preempts the low priority process. And remember from our discussion of deadlock that we sort of have this, you're not required to release your resources when you're preempted or when you're blocked by another process. So in this case, L is still holding its lock on the resource R. Okay. Then high tries to lock R as well. Now we have this weird situation because we'd like L to let H run, but H needs something that L holds. So what can we do? Really, all we can do in this situation is just let L run until it finishes. The only problem is that if another process higher priority than L starts running, but not as high as H, then that thing can basically run indefinitely. That can completely prevent H from ever being scheduled or ever getting the CPU again, because it will prevent L from ever getting back to the CPU, finishing with its locked resource, and then going on and doing other things. Now, I talked about lock-free data structures last time, and you can imagine that lock-free plus priority scheduling, maybe you could come up with something really clever there. But if you can't get away from having locks, then locks plus priority scheduling can easily suffer from priority inversion. It's actually surprisingly common how much people have to deal with this issue. Okay, everybody got the scenario? So that's the scenario. Let's check on the time, make sure that I don't run away. Yeah, so L is preempted by M. It can never finish, so blah, blah, blah. Now, the reason why this is so problematic is that usually they're high priority tasks because they are required for the system to continue running properly. Okay? So oftentimes priority inversion can really destroy the effectiveness of these systems. And the great example is Mars Pathfinder. So I don't know, again, this may be, well, it's probably not before your time, but just approaching. And Mars Pathfinder was really interesting because it was a huge success. I think that was the first one that JPL sent up that would like actually bounce around on the planet and then open up. So it had these inflatable balloons on it and parachute, and so it would land a certain distance and then bounce and open up, and then the little rover would drive off. And the issue was, we saw in the news, this thing keeps rebooting and we don't know why. So that was what we were seeing. That's what the nightly news would say. And JPL was dealing with this serious problem. Okay. The cause of it was that you had a high priority process that was responsible for making sure the system was actually alive. And typically they're called watchdog timers. A processor will actually have it. It's basically a timer that either counts up or it counts down. But when it goes through, like, it counts all the way up and then wraps around back to 0, it forces a system reset. Okay? And the idea is that when you have this watchdog timer, so it's counting up, what you want to do is have a software interrupt, a software timer interrupt, that will reset the watchdog back to 0. And so the idea, as long as the software is running properly and that timer keeps kicking off, then you can reset the watchdog timer and it'll never wrap around. But if the system wedges somehow, so you end up in a state where everything's halted and the system is just messed up in some way, well, the watchdog timer will keep ticking up, and then finally, boop, it goes back, system resets, and we don't have to send a human being to Mars to push the reset button on the Pathfinder, because it has hardware to do that for us. Okay? So that was the idea. High priority process responsible for resetting a watchdog. There was a low priority process. I can't remember what it was doing, but it happened to share a lock with the high priority process. Okay? So that was the problem. The low priority process could lock something and prevent the high priority process from acquiring the lock. Then we had a medium priority process, and this was doing something like climate measurements, which took a long time, or sending data back to Earth, which also takes a long time. And so the medium priority process was preventing the watchdog timer reset code from running. And so even though the system wasn't hung, the hardware thought it was, and so it would reset the Pathfinder. And this was quite a big problem. Everybody got it? So that was the issue that was coming up. How do we solve this problem? Well, it turns out that there's a number of interesting solutions, and they have varying levels of sophistication and correspondingly varying levels of interest. One is random boosting, which I don't know, is a little bit. It's an ad hoc approach. That's why I don't like it. Is I would describe it as ad hoc. If I see a process that's waiting, then I'm going to go ahead and boost the priority so that maybe I can get it above something else running, and that'll sort of kick the system out of a priority inversion. Okay? It's an approach. I don't like it at all. I like systems where they're predictably going to be good, and this doesn't look like it's predictably anything. It's except predictably unpredictable. Then you have priority ceiling protocols, and this one's kind of a fun one. Basically, when you have those resources that processes lock, you give each one of them a priority. And when a process locks that resource, they automatically get that priority. So L, if the resource R was given the priority H, then when L locked it, it would automatically have the highest priority. And it would be above M, it would be able to run to completion, and then H would be able to continue on, and it would be perfectly happy. Okay? So that's priority ceiling. And this is a great approach. This is very fast. You guys, again, if you have gotten to the point of doing your priority donation code, then you're probably seeing all the little details you have to keep track of. And it's like, I want to lock this thing, it's not available for me to lock, so I've got to go and chase down all the dependencies and figure out who do I donate my priority to. And so then you have the base priority and the computed priority, and you've got all this stuff to compute. Well, that's expensive. This does a really simple version of that, but you have to know beforehand who else is locking stuff. Okay? So that's the priority. Figuring out the ceiling is the complicated part. You do that before runtime. Then you have priority inheritance or priority donation, which is what you're implementing. And so basically when you want to lock something, if it's not available, you donate your priority to whoever's holding that resource. And so that's the idea here. So the process's priority is basically the maximum of its priority plus everybody that it's blocking. Okay? And so priority inheritance and priority ceiling are two different versions of the same thing. This is really flexible, doesn't require any thinking at compile time or design time, but it does all its work at runtime. This one, easy peasy at runtime, but you have to do all your thinking beforehand. Okay? So you can imagine priority ceiling would be very efficient if you had a very time-sensitive system that you were building. Questions? All right, so there's that. Priority donation. Okay, so this is always fun. You have a few challenges that you have to think about, which I think, thankfully, you guys don't have to. I think that you were told in the write-up that you don't have to deal with certain really nasty cases. Okay, so block processes can form a chain, so this is one thing that you have to figure out. So process 1 locks a resource, process 2 locks another resource, then tries to lock the first resource, and so forth. You can basically make this as long as you want. Okay? So you basically have to chase down that chain and donate your priority to all the blocked processes. Okay? This definitely adds up time. And you'll notice here, I say here that the Mars Pathfinder was running an operating system called VxWorks. VxWorks is used pretty commonly on embedded systems that need to do a lot of computation and so forth. And it has a priority scheduler. That's how VxWorks works. And it turns out that it's used on a number of JPL projects. And since priority donation is expensive and slow, we'll turn it off so that we don't have to deal with the overhead. And so the Pathfinder was sent to Mars with priority donation turned off. Okay? So basically, the fix to the Pathfinder rebooting was, because I think I may have mentioned this before, I can't remember if I have, but they had an identical copy of the Pathfinder on Earth that they could use for testing and making sure everything would work properly before they sent things millions of miles to the Pathfinder on Mars. And they tried turning on priority donation, see if the Pathfinder still works, test it out, exercise it. And once they were reasonably confident that they would not break everything, then they sent the command to Mars and turned on priority donation on the Pathfinder on Mars. And it worked flawlessly ever since. Okay? So that was an interesting issue that sort of arose. It's challenging, right? Sometimes, I don't know. I don't know why their test harness didn't sort of apply the kind of slow things going on that they encountered on Mars. It seems like something they could have identified and avoided. They probably have that now in their processes. Okay, let's see. So priority donation and deadlock, another way that things can fail. So you have two processes, two resources. They each lock a resource, and then they each try to lock the other resource. Okay. Well, now you have a cycle in the chain, and a naive kernel, if it just followed that chain without trying to detect whether it's visited a particular node before, you could have it hang. You could basically have the kernel hang. And nobody likes a kernel that hangs. So you could circumvent this. You could easily have it detect deadlocks or cycles. It probably would be cool to have that as a debugging feature that you could turn off after a while once you were convinced that it's probably correct. Because that's one of the things that's fun about concurrent systems. I haven't seen a deadlock yet. You can't really assume that that means you never will. You can really only assume that if you know the design is correct or if you're able to prove it correct. So anyway, but you could certainly do that, but then that increases the overhead of priority donation. Okay, so that's those are some of the challenges with priority donation. Any questions? So you'll get a lot more interesting details about this as you dig through the implementation. There's certain optimizations that you can take advantage of in the design of your data structures. A process, or I should say a kernel thread can hold multiple locks. So there may be multiple kernel threads that are waiting for a particular kernel thread, but a single kernel thread will always be waiting for only one other kernel thread, because you can only lock one thing at a time. You can only try to lock one thing at a time. And you can use that to optimize the design of your data structures. Okay, multi-level queue scheduling. So this is the other one that I want to talk about, since you will need to think about this. Processes do vary in their behaviors, and you can sort of classify or categorize them based on those behaviors. Here's a couple of ways that processes can be categorized. I want to mention that these two examples are overlapping. So it's not like this is one, and then these are additional categories. So foreground processes would include, for example, both of your interactive processes. Background processes might include system processes and batch processes. But you can see that they have different needs. Like, how quickly do I get this? Like, is it okay to have long latency? When I become ready, do I need the CPU right away? Can I wait? How long do I expect to hold the CPU for? And you might expect batch processes want to hold it for a lot longer than system processes. So these different categories have different characteristics. And so multi-level queue scheduling is all about creating static queues to put these things in. And then the queues are prioritized. And within each queue, you basically do round-robin scheduling. And whatever the highest priority process gets the CPU, and then so forth down the list. Straightforward. But notice what I'm saying here. This is multi-level queue scheduling. In CS24, we talk about multi-level feedback queue. This is static, and it doesn't really adapt to processes changing behavior. So they are permanently assigned to a specific queue. Not very flexible, and so that's why, again, this approach is not really heavily used. Okay? It's simple enough, but it, with just a little bit more sophistication, you can create something amazingly powerful. Okay, so categories and priorities for processes. Yeah, so you would say system processes are highest priority, and then you would categorize everything else as one would expect. Okay, so almost invariably, the high priority queues always preempt. So if there's a available process to run in a high priority queue, it always preempts a lower priority process. Okay, and so notice what this means. You stop executing the high priority queue when those processes have all blocked or terminated. Okay, that's basically just how it is. You block on the timer, you block on disk I/O, maybe you block on the network, you're waiting for a request to come in. There's no reason to occupy a CPU. And then the system says, okay, now I'll start executing lower priority things. Okay, so again, you have to design this carefully. I don't think, you may still be able to do this if you bring up the Windows Task Manager. You can go in and you can set the priorities of things. And it's real easy to make your system completely useless by setting something to be ultra high priority and just make it preempt all the other important things going on. So, the system becomes sluggish and unresponsive and it doesn't do anything useful. So when you have these kinds of designs where things are fixed static priorities, it tends to be that you have to design them carefully to make sure that they actually achieve the responsiveness and the performance that you really want. So that's the challenge with this stuff. Another thing that you often see in these systems is they may just divide the CPU time across some subset of the queues. So they may say, I really want to devote most of my CPU to running user interactive processes. And up to this percentage can be used for system processes. But really, I want to devote the bulk of my CPU time to user processes. Because remember, computers exist to do useful work, not to do upkeep. That would be boring. Okay, yeah, you can have various scheduling algorithms. That's all very exciting. You can tune the scheduling algorithm for a queue based on what is needed, so that's no big deal. Okay. We're not going to talk about that too much. I don't think it's super exciting. And fortunately, it's not something you all have to deal with in Pintos. So you can read about that if you want, but it's not that exciting. It's really common for processes to change behavior over time. The examples that I love to use are like MATLAB, right? You're typing in MATLAB, so it's interactive. And then you start running a computation, and suddenly it switches to compute intensive. So, and there's a lot of other examples you could come up with. So you have to be able to adapt to these kinds of situations occurring. And, Photoshop is a great example. Oh, media transcoding. I do that every time I lecture, in fact, because I record the lectures and then I convert them to a usable format. Because the default QuickTime recording is ginormous and nobody wants that file. So basically, you have a user interface, you take user interaction, and then you go do something long-running, compute-intensive. Well, you've got to make sure that the OS can respond properly to that change in behavior. And so this is where multi-level feedback queue scheduling comes into the picture, because basically, if we see process behavior change, then we'd like to respond to it in an intelligent way. So we'd like to favor short jobs. Okay, we're expecting short CPU bursts. We'd like them to be high priority. We're expecting they're probably interactive. We like processes that block an I/O. That makes us super happy because they free up the CPU for other processes. And we will observe behavior and then categorize them. We'll go ahead and put them into different queues based on their observed behavior. Okay, this is the one we all know and love. Now, quick question. Let me see what time it is. Yeah, 1:50. We have time. Are these things necessarily always multiple queues? It may be that you just have a single queue and you have some queue number that things are sorted on, so that you could do that kind of thing. Or you might, like Macs are interesting because they actually have 4 priority bands, and so that could be emulated by having 4 queues, 1 for each priority band, and then processes sorted in each band. Okay? So the reason why I say that is because sometimes when people implement the multi-level feedback queue on Pintos, they'll do 64 separate queues. Complicated. Okay? You could also just do a single queue and keep the processes sorted. And that tends to be the recommended approach because it simplifies the management of all of these processes. Okay? So I'm going to drop that as a hint. Let's see, what else we got here. So yeah, you have a FIFO. Well, just like I was saying, you can think of this in concept or in implementation. It's up to you. But each FIFO has a priority associated with it, and the processes in higher priority FIFOs preempt the ones that are in lower priority FIFOs. Okay? Now, there's interesting details about this. New processes are added to the end of the highest priority queue, so they go down until they slot in wherever their behavior dictates that they should. If a process happens to be preempted, so its time slice is up, then the kernel just got a big signal that it's not in the right queue, so it can bump it down a queue. But if it yields or blocks before its time slice is up, then it can stick around. Now, there's one interesting detail about this. If I yield or block, where am I going? If I yield, I'm going back to the ready queue somewhere. Okay, so that's okay. But if I block, I may be stuck into a completely different queue. And so one of the little nuances of multi-level feedback queues is that when a process is blocked, it needs to remember what queue it came from so that the kernel can put it back in that queue again. Because you don't want to start way back at the top again. You want to go back to the queue you were in, okay, when you become ready. So that's one of the little nuances about this, is that you need to think about where the process was when it was ready so that when it goes back, it can go to the right place. Okay. Yeah, and that's not very exciting, but that certainly can be done as well. Okay, yeah, there is a lot of flexibility in this. Like I was mentioning, Macs have an interesting approach where they have 4 priority bands, and you're always stuck in that band, but your priority can change within the band. A lot of times, different bands will have different schedulers. So you might have a real-time band or a real-time range of priorities, and the scheduling algorithm for that will be a periodic real-time scheduling algorithm, not a round-robin algorithm or something like that. Okay, so you have various interesting details like that. You can read that other stuff. So yeah, this is a very common approach because of how flexible it is. So just to mention this, and then we'll actually be done for the day, which is good because we're about time up. Windows NT all the way up to Windows 7. I don't remember. I haven't heard anything about Windows 8 and 10, but I would not be surprised if they have a similar approach because Microsoft is not really very widely in this way. But basically, you can see they have 32 priorities. And they have a band for real-time processes and a band for normal processes. Okay. OS X also has various queues for processes, but they're again grouped into bands. You have normal, which would be like your applications, Emacs or Excel or your Chrome browser or whatever. System, kernel mode only, and real-time threads. So it's funny that iTunes comes in higher than kernel mode, which is pretty funny to me. Okay, and threads cannot move outside their bands. FreeBSD, NetBSD, lots of queues. And Linux, I don't have it here yet. Linux used a multi-level queue all the way up to Linux 2.4. And then it started doing really fun stuff. And let me just ask, does anybody have any questions about multi-level feedback queues or multi-level queue scheduling? Pretty straightforward, right? And I mean, we talk about it in 24 as well. So at least that part is obvious. Although 4.4 BSD computations can be a little bit confusing. But what we're going to do next time, and this is why I'm excited about Monday, is we'll talk about real-time scheduling. And there's some really cool issues you run into with real-time scheduling that we'll talk about. And then we'll also spend the last part of the lecture talking about the various approaches that Linux schedulers have taken since the 2.4 kernel. And there's some really cool ones. So that's what we'll talk about next time. Okay, we'll see you Monday.